So, good afternoon, everyone. I'd like to present some highlights from LHCb. Um, let's get it started. So I'm just gonna, as usual, present you the experiment, the current status, and then talk about our contributions to both the detector itself, and then showcase some of the most recent analysis of the past few years. But I'd like to illustrate the not old, but the primordial interaction of the Brazilian groups in LHCb. This is the LHCb week. The last time that an LHCb week happened in Brazil is in Curaçao in 2001. There are some people in this room in this picture, and this is actually a very important LHCb week in which big decisions were made about the design of the experiment itself. Oh, it moves. Okay, great. How does this go? No, it doesn't matter. So the LHCb detector is a forward single arm spectrometer. Now we call it general purpose forward detector. It was originally built to mostly measure B and C quark decays, but we learned that we can do pretty much every type of physics here, from WMF measurement, electroweak, and so on and so forth. So you have the collision point right here, and you see you have about half of the detector. And as the particles are created, they traverse all of these different detectors, which go from tracking. You have a magnet station, then you have two Cherenkov to allow you hadron identification, colorimeters, and then finally muon stations for muon identification. So we have excellent vertex resolution, which is necessary to precisely pinpoint decay vertices from particles created on the primary vertex, and also excellent momentum resolution, which is given to us by the trackers on both sides of the magnets. And we're going to talk about these in a second. Boop. No. Boop. Boop. And yeah, I'm too anxious. So the Atlas and CMS, we're talking about the high lumen LHC, but for LHCb, the future is now. So you can see long shutdown 1, long shutdown 2. You can see this is the accumulated luminosity that we took with our experiment. And from 2019, well, really 2018 to 2022, we had our big upgrade. And with that, we were able to multiply the instantaneous luminosity by a factor between 5 and 10, which means that this line goes up much faster. Our statistics increase 5 to 10 rates. Not only that, but I'm going to describe in a second, we also greatly improved our trigger setup. So at the end of 2025, which we are just ended the proton-proton run now, we have a total of all lifetime of the LHCb experiment. We got about 31 inverse femtobarn, which 2/3 of it were just in the last few years. We expected to reach 50 inverse femtobarn at the end of run 4, but with the addition of 2026 and then run 4 on top of that, we're probably going to go over it. And all of that led to over 600 papers published. So I'm going to just pinpoint 2 contributions that our groups have done to LHCb in particular. First is the vertex locator, so the Velo, that first detector that I showed you. So we have here a CAD drawing of what the detector looks like. The beam goes into the screen, and you have 2 halves, each one with 26 of these modules here. So these modules were all constructed basically artisanally, assembled, and then shipped about 1,000 miles from England to the UK, where it was hung upside down for a few excruciating minutes and then put right into the beam pipe. This detector reconstructs every single vertex, proton-proton interaction in LHCb, and we read out every single hit that is generating on it. So that's the big improvement LHCb delivered in this upgrade, is that we don't have a hardware trigger anymore. We read out every single signal, which means that we can be much smarter on our high-level trigger. So UFRJ was involved with this in the sensor R&D. and it supports heavily the operations and the quality of this detector. We also had contributions to the scintillator fiber tracker, the Sci-Fi. So this is the other half. I'm not going to learn how to use this. This is the other half of our tracker. So here you have the first part of reconstructing your particles. Here is the second. And it's made out of these mats, which are fibers, optical fibers, but they have scintillating dopants on them. So when particles go through, they generate light, which is then read out by silicon multipliers. These modules are quite large. So you have a total of 30 square meters. And you can see here, it's like about 3 persons high. And it's 128 planes. So you reach 80 microns of spatial resolution on these ends with heat efficiency better than 98%. CVPF, the place we are in now, was heavily involved in the firmware, without electronics, and also the operations of this detector. Cool. So what do we do with this? So here I'm going to show 3 recent papers. First is recent measurement of CP violation in the decays of B mesons into 3 hadrons. So right here on the left, you can see 4 plots with mass, and you can see on the legend, you can see that you have either 3 pions or kaon and 2 pions. And the difference between the left and the right, you can see that the heights are slightly different, and that's CP violation manifest right here on you for us to see. You can see that you literally see less of one kind of B meson than the other, depending if it's matter or antimatter. But not only that, we can study how this CP asymmetry is distributed in the phase space. How do we do this? And hold on a second. If you don't know Dalitz plot, you're going to learn it now. So the particle decays into 3 bodies, and you can reconstruct the mass of each pair of particles. So here you get one of the kaons plus a pion, and here you get 2 kaons, or you get 2 pions and 1 kaon pion. Here you're going to see all the resonances that go through the process of decay of the B mesons. And what you see on the Z scale is how asymmetric for matter or antimatter that region of the phase space of the decay was. And so here we can investigate if there's any particular source of CP violation in the phase space that could even be hidden by another asymmetry in the other direction. What we see is that there are heavy asymmetries in some parts of the phase space, and now we are trying to investigate and understand if this is true CP violation or is some kind of hadron effect, some hadron rescattering. So now that we know what Dalitz plots are, we're going to look at them in the decays of charm mesons. So before we're talking about B mesons, now we're talking about charm mesons. So in the center model, we do not expect to see CP violation here. So we expect to be very small, 10 to the minus 3, in this particular transition. So we look at decays of the D meson in 3 bodies, the same way I described before for the B meson. But you have a difference here. You see that this Dalitz plot, this oval-shaped plot, has a much higher resolution. That's because this kind of charm decay is very abundant in LHCb. So we have a beautiful amount of statistics that shows you every kind of resonance possible in this decay. So this is a run-2 analysis filled with 5.4 inverse experimental Barn of data, so the first up to 2018 of data. And the results we obtain here is that they are consistent with CP symmetry, which is expected of a standard model. But this is also the most precise measurement of this kind, given the statistics of this charm. Here you can see the measured asymmetry. This is the analogous to the previous analysis result. You can see they are all within the standard model, 1 or 2 standard deviations from the standard model. Last but not least, we're going to talk about the exotic states seen in the center exclusive production in LHCb. So what is center exclusive production? Is when you have a proton-proton that collide, but they don't dissociate. So you have just an exchange of pomerons, so gluons or photons exchange, and you generate a single J psi particle or some other kind of particle. And you see nothing else in your detector. So in order for you to reconstruct this event, you can't have like 20 proton-proton interactions at the same time, because you need to know that you saw nothing else from this particular proton. How do we do this? We have a tiny LHCb here, and then we put scintillator detectors, which are part of this Herschel detector, which are in the Roman pots, several, like tens of meters away from our detector. And then there we can tag whether or not that proton has dissociated. And we look at the events in which it has not. So what we do is to reconstruct the mass of the J psi and the phi, and then reconstruct the object. And here you see an incredible amount of structure. So this structure, you can see here all these states. These are all tetraquark states, exotic states. And this is the first time that they were observed being produced directly, not within the decay of a B meson. We were also able to extract bunch integrations from each one of these events as well. So in conclusion, we have deep involvement of Brazilian groups in LHCb since its inception. And we have sizable contributions for the upgrade program and continuing interest into strengthening our whole role onto the next upgrade. And we have a wide range of physics. Since I have 3 minutes, can I ad lib one more point, which is the future? So we just installed our upgrade that I just told you we're going to run for in run 4 and run 5, right? For run 3 and run 4. And in run 5, we're going to do something yet more daring. We're going to add timing to every single detector to operate with even more collisions. So we're going to go to 50, 60 proton-proton collisions per bunch crossing, which is where Atlas and CMS are now, when we're looking at them in an incredibly tight angular spectrum. So both CBPF and EUFRJ are looking heavily into how to participate in the tracking upgrades. On the VEL upgrade 2, it involves timing at each pixel level, and a Mighty Tracker, which involves HV CMOS and new technologies for large area silicon detectors. That's it. Thank you.
Thanks a lot to Vinicius.